study, everybody showed you the Nehalem architecture. Some of you even had the chance to review and touch it, Linfield and the desktop. Let me say, first of all, in one sentence. Nehalem architecture, Linfield architecture is a great architecture, but it's even better when you look at the mobile space. And I'll explain why it excels. First of all, I believe you heard the TikTok story, and we'll continue to say it until you say tick-tock, tick-tock. The talk is the new architecture. The tick is the compaction and integration. We're trying to make sure that we are not merging the two together because the risk is huge. A new architecture, a new process technology, then Nehalem is a talk. Stable 45 nanometer architecture, totally new. A stable 45 nanometer process technology, totally new architecture, so the risk in the architecture is not the process technology, and later on I'll take you over to Westmere, which is the 32 nanometer compaction. If you are trying to see, actually the architecture was supposed to span everything from notebooks to bigger notebooks to desktop and to servers. And if you look at the next generation after Sandy Bridge and other products that we are going to see, it's the same idea. And the question is, how can you scale an architecture all the way from notebooks up to the server? And the answer is very simple. By the way, in 2003, it sounds strange. The biggest limitation when we were working in the Pentium 4 era, if you remember, we couldn't have taken it and shrink it from power point of view into the notebook space. It was too thick, too hot, and the battery life was challenged. And we came with the terminology at that time frame. We hit the power wall. We need to design something new for notebook because we hit the power wall. The power wall is not a notebook terminology anymore. We hit it in the netbook. We hit it in the desktop because if you want all-in-one, you want a small, sexy form factor, exactly the same power wall. You don't want to hear the fan all the time because it will annoy you. You want this, again, and if you look at the server, the bigger problem in the farm, how the hell do you get the electricity in? How the hell do you dissipate the heat out? So power efficiency is relevant all the way of the scale from the beginning up to the high-end computer or servers, and that's what the architecture is trying to do. I shared with you in the past, and I'll not jump into it, we went from a 3-chip solution to a 2-chip solution. We always kind of put our focus on the huge caches. We've got this technology advantage that enable us to have a great cache, so when you run locality, you can get great performance with the caches. But when you've got these 4 crazy cores that are consuming so many MIPS, this is not good enough. You need also to have a wide bandwidth, and we integrated the memory controller. Now we've got the goodness of the two worlds. We've got a great bandwidth for the memory controller. I'll share with you some benchmarks. And on top of it, we've got a huge cache that will give you the locality, will give you the quick access in case the data is inside the cache, and I believe we'll enjoy the goodness of the two worlds. And this is the architecture. The thing that Daddy showed you when he introduced it, in everything would say, guys, this is the performance, it's 2 gigahertz, that's what you've been used to do hectare 1, and the turbo. And the turbo, as I mentioned, is what is the extra boost that you can get from this core if there's power available to do it. And that's a very important thing. If there's power available, and if you're not jeopardizing the quality or the reliability of the chip. And I'll do a deep dive with you to show you how we look at each one of those, because if you turbo boost the microprocessor, but the life will be 3 years rather than 7 years, you definitely didn't do too much of a good. So there's a lot of reliability concerns that need to be taken into account when you are trying to turbo boost microprocessor. So we introduced the Clarksfield, the quad core, and it's supposed to be today. You'll read about it, but the more interesting thing, it's not that you're going to read about it, actually it's on the shelf. And I encourage you later on to come over here. What you see over here is a Clarksfield systems. All the systems are Clarksfield systems. We've got here a system from ASUS. We've got a system from Lenovo. We've got a system from Cosmio, which is Toshiba. We've got this slick system from HP. Very interesting design. You can touch it and you can see it. We've got a system here from Sager, which is a US OEM. And we've got another system over here from Dell. So actually, if you look at all the major manufacturers, they already have it. Very easy to identify. You just hit alternate control delete. You look at the performance monitor. You see that you've got 8 threads. And you know, okay, this is Clarksfield. So I encourage you to go later on, touch it, look a little bit at the responsiveness. This is really beautiful systems. And again, these systems are going to be available. I don't know how fast it will go into the channel. I'm sure that some of them will be available pretty soon. Some of them, but definitely this will give you totally new experience. And I'd say which is the new experience that I'm going to talk about. So as I said, when we speak about it, you'll see this is the frequency, this is the turbo, this is the frequency, this is the turbo. Let me make a deeper dive than before and say why do we believe it's important. First of all, if I'm trying to go for a 50,000 about this architecture of Nehalem, I believe there are a few things to mention. First of all, the turbo boost technology, which again, I know that some of you are journalists going to write article, so I don't want you to suffer this evening in the hotel trying to figure out what's the headline. Just use Intel Turbo kick ass. Or I can help you, if you are more politically correct, I'll help you, but definitely it's a lot about the turbo. And I'm going to enjoy it because if you don't have turbo, you might be a little bit disadvantaged, and I'll help you to see what is the disadvantage that will help you. Not that I'm alluding to any competition or anything like that. So we are going to have the turbo boost technology, the hyper-threading, that you can run 2 threads in parallel on the same core in order to accelerate the application if you run either application which is threaded or you're running more than one task. We've got the dynamic power management, and the whole idea is to reduce the leakage as much as possible to get long battery life. And the more power I can cut from some part of the technology, I can move the extra power to something else. And the enhanced cache architecture and integrated memory controller, which I'll not touch too much, but definitely the level 3 cache, the 8 cache, all the inclusion with respect to the level 2, level 1, all the way that we added extra bit to make sure that we do smart snoop so we don't wake up the caches when we don't need to snoop it. If I have some time, I might try to touch it later on. If not, I'll be glad to do it on a one-on-one. But this is the core, and we've got 4 cores. If you've got full-threaded application or several tasks, you use all the 4 cores. If not, you try to switch them off. Now, how can you switch a core off in doing 2 things? First of all, when you switch it off, you want literally almost 0 leakage, which means that the effective channel length of transistor cannot be minimum L effective because it will leak like hell. On the other hand, when it's on, you want to make sure that you don't have an IR drop, because if you have IR drop, you reduce the frequency and the ability to work with the chip. So actually, I believe that we owe here the credit to the technology guy that developed this switch, this sleep device, which is a huge device. Again, for the designer of you, know what is Z over L. Z is the width of the device, L is the effective channel length. If I take a normal memory logic device with the minimum Z over L, that one that does all the calculation and everything before you go to the buffer, Z over L, the switch devices, the Z of them, the length of the devices of the Z devices is 5.5 million times bigger than a normal logic design. Try to imagine the width of a transistor, which is 5.5 million times bigger, trying to put it in your manufacturing capability without having defect and without killing the yield of the product.